Hello guys, and welcome back to the channel. I'm Innocent, and in this video I'll be talking about quantum computing and cybersecurity, preparing for the impact of quantum computing. This is going to be a kind of introduction to quantum computing, the beautiful nature of quantum computing, and how a lot of people see it as magic. And honestly, when I try to wrap my head around quantum computing, all I can think of is magic. Or, of course, there is a science behind it, but I mean, just thinking about it and the possibilities that exist with quantum computing blows my mind. It's truly magical. And in this video, I will simplify what quantum computing is and um, its relationship with or to cybersecurity. Okay, so that's what this video is all about. It's going to be a fun-filled video, and I guarantee you that you will learn something from this video. So let's go. What exactly is quantum computing? Okay, I'm trying to. Okay, yeah, okay. Table of contents. I'll go over introduction, understanding quantum computing and cybersecurity. So I'll look at the threat landscape, and when I talk about the threat landscape, I will talk about things like cryptography and how quantum computing is a kind of computing, or a quantum computer will be powerful enough to actually hack into any system that currently exists today. Okay, and I'll also talk about the future of quantum computing and draw this whole presentation to a conclusion. So, introduction: classical bits versus qubits. Now, when we say bits, okay, from the word classical bit, what do we mean? The computers that we use today, as it were, this is 2015, and the classical computers we use, your laptop, your mobile phones, any kind of computer really, operate based on bits. Okay, classical bits. And this classical bits is contains 0 or 1. Okay, one state at a time. What do we mean? Imagine, of course, I have this image here which properly depicts the whole thing. So imagine a switch. At every point in time, the switch can either be on or off. Okay, and that is how your computer systems operate, right? So if you want to if you look at the if you look deeper at the structure of a computer, a classical computer, you will see that it's made up of zeros and one. So everything you are seeing as on your computer gets to convert it to zero or one each time, and that is how the computer communicates with you, the human, or me, the human. Okay, so think of it as a single choice checklist, yes or no, at every point in time. Computer can either make a zero decision or one decision. It's either on or off. Now, this is the classical bits that make up your computer. Then we also have what we call qubits. In quantum computing, or in a quantum computer, we have qubits. Now, qubits have the ability to be a zero and one at the same time. Okay, so again, it's a kind of brain taxing if you are new to quantum computing. But let me try and look for a very simple example to really expatiate and explain what we mean by this qubit. So supposing you have a box. Okay, supposing you have a box, and in this box you have some you have what do you call it, let's say you have some toys in the box, and you can either pick one of these things to make or build a structure, right? And at every point in time, you have the opportunity to pick one and then make your stuff. But we are saying that in quantum computing, everything, you can do everything at the same time. Okay, so again, qubits um can be zero, one, or both at the same time. So like a coin spinning in the air, it's just the heads or tails until you catch it, right? So if you spin a coin, imagine you're spinning a coin, and as the coin is spinning, it is bouncing at the same time. So imagine that in your head. That's how a qubit operates. The only time you can have a particular position is when you get hold of it and look at it. That is when you can have a particular position on the qubit. All right. So let's continue, and we have a quantum revolution. So this is important because quantum computing leverages qubits, like I said, superposition, and entanglement to perform complex calculations at unprecedented speed. So when we say superposition means that it can exist in multiple states at the same time, while entanglement means that if you have one qubit here and another qubit there, they can communicate with each other. Okay, so that's what we mean. And these properties allow us to perform really complex calculation at, trust me, unprecedented speed. Okay, and we'll see this as we go on. So there's what we call dual nature, and a threat to current cryptographic system, and a tool for enhancing security. And when we say dual nature, we mean that quantum computing can be a threat, or it can be a tool for enhancing security. That means it has both negative and positive use cases right now. So let us look at this research question. What are the implications of quantum computing for cybersecurity, and how can we prepare? Quantum computing for cybersecurity and how can we prepare is the question we're going to answer in this presentation. So understanding quantum computing. I love this image here, by the way. Credit to Microsoft Designer AI. All the images on this slide were generated using artificial intelligence, right? Microsoft Designer AI. So credit to them. Right, so let's look at the principles of quantum computing. Like I said before, superposition is so quantum qubits exist in multiple states, which I said previously, and it does that simultaneously at the same time. Now qubits explore all possibilities at once. So for example, a 3 qubit system can represent 8 states simultaneously. That is 2 raised to power 3. So it can represent 8 states simultaneously. Then there is massive parallel processing power. Okay, that means it's very powerful. That's what it means. Then we have entanglement, which I said linked qubit enable instant state correlation. Qubits linked across distances, change one and the other reacts instantly. Okay, Einstein called it spooky action at a distance. So let's look at interference, amplify correct solution. That is one of the principles of quantum computing. There's interference, which means the correct solution is always amplified, right? If a computation is being done by a quantum computer, it will always amplify the correct solution. Another benefit, another advantage. Now, current state of quantum computing. For the current state of quantum computing is actually in its early stage, but is growing. Then the qubits already exist. We have IBM, we have Google and others that run 50 to 100 plus qubit systems. Although 50 to 100 plus qubit systems is good for development stage, but by the time we start to think of large application and use cases for quantum computing, then we need quantum computers with more qubits. Okay, thousands and millions even of qubits to actually implement some of the theoretical experiments that are currently ongoing in the quantum computing space. So what is the challenge? Noisy and unstable. NISQ era, that's noisy intermediate scale quantum. That is what NISQ mean, and we are in the NISQ era, noisy intermediate scale quantum. What about power? Cannot yet break RSA, but Shaw's algorithm looms. Now, RSA is um, one of the leading cryptographic algorithm that's currently being implemented in crypto systems, right? So we are talking about banks, we are talking about military, we are talking about hospital, healthcare, and just general protection of user data. RSA algorithm is one of the system for encryption of data, right? Public key cryptography. And we are saying that this quantum computing, although it cannot at this moment break RSA, but it is very close with the Shaw's algorithm. So think of encrypted government data, and let's say we have a powerful quantum computer. We are saying that if we have a powerful enough quantum computer, RSA algorithm will be a piece of cake to that computer in terms of what decrypting encrypted information, right? So think your banks. So your information may not be safe in the next 10 to 20 years if what the recommendation in this presentation is not being affected by that time. So what will be the recommendation? Watch this video to the end. Now, what of cybersecurity impact? Post quantum cryptography, right? E.g., NIST standard is also already in development. You see that? So we are talking about post quantum crypto in development in terms of cybersecurity impact. That's what we have. Then timeline, practical supremacy, maybe 5 to 15 years. Okay, so in 5 to 15 years, we should have working. We already have quantum computers. Don't get me wrong, but we should have quantum computers on a large scale. Okay, based on the projections of having hardware that is powerful enough to support those qubits, right? Then we have challenges. We have decoherence and error correction. Right now, it's not stable. So the quantum computers we have are not stable. So of course, there is a lot of work with IBM and Google going on and trying to stable the results of these quantum computers. And once this is achieved in the nearest future, a whole lot will change. Okay. Then let's look at potential application of quantum computing. We are talking about cybersecurity. So for cybersecurity, we have breaking classical encryption. Shaw's algorithm threatens RSA, ECC, and Diffie-Hellman. These are crypto algorithms. Okay, and post quantum cryptography, that is quantum resistance algorithm, e.g., Kyber, dilithium for future proofing. Okay, so there is actually quantum resistance algorithm that all people are also working on. There is quantum key distribution, unbreakable key sharing via quantum mechanics. Okay, and again, this is also trying to build quantum resilient systems in case of the future, right? That's what it's all about. Improved randomness. So true random numbers generation for stronger cryptography. We have quantum safe authentication, new methods like quantum resistant, zero knowledge proof will definitely be developed. Algorithm optimization. Grover's algorithm enhances threat detection and cracking. So, of course, there is what we call a threat detection system. There's also what we call intrusion detection system. So, this algorithm have the ability to search database with the like very very fast, and is able to quickly detect threats, and is very applicable especially in intrusion detection systems. So If we have such system, then we are very close to building, you know, hack proof systems, that system that cannot be hacked, basically. So we'll be very close to that if we have this algorithm optimization. Then there is attack simulation, faster modeling of complex cyber attacks, and this is applicable in the area of the red team hacking and the penetration testing. So if we are able to implement some of this attack simulation, especially for penetration testers, then we can have better security for the systems. Then what about the challenges? We talk about scalability, transition cost, and dual use risk. Those are the challenges that we currently face with quantum computing. Now let's look at the other side, which is the general application. Quantum computing can also be applied in other fields like medicine, drug discovery, logistics. For medicine also, apart aside drug discovery, we can also use the quantum computing will also be very useful in things like genome analysis. You know that when we are talking about genome, we have a very large data set, and of course, the classical computers are doing a lot in terms of such analysis. But imagine what quantum computers will be able to do at a faster rate. So we would have a cure for so many diseases, right? We have a cure for so many diseases with quantum computing. And logistics, supply chain optimization. Imagine, let's take like the Uber and all these things that are into logistics and supply chain, and imagine quantum computing being able to analyze a whole data of the whole world, very fast. And all these things are being incorporated into applications, right? So we have AI, enhanced machine learning. Of course, you know that the success of AI is really you know dependent on, number one, availability on data and computing power. Okay, so if we have enough computing power that we can find in quantum computing, then we can have enhanced machine learning and build models that, as a matter of fact, I don't think we can really fathom the level of sophistication that these models will actually have. So that's that. We also have the threat landscape, so vulnerabilities. So vulnerabilities is current cryptography. Quantum computers can break RSA and ECC using Shor's algorithm. So that's what is there. Then, of course, RSA and ECC are cryptographic algorithms that are very popular. Then we have, of course, threatening sensitive data, government, finance, healthcare, risks to data security. So the risk is that we can harvest now, decrypt later attacks. So what's going on is a lot of malicious actors are now harvesting data. So they launch an attack, harvest data, and store this data for when quantum computers will be mainstream and those data will be decrypted. Okay, this is very dangerous for data sets that needs to be data sets where what do you call it now, the privacy needs to be sustained for a long period of time. So if you have such data sets, for example, medical records, healthcare data sets, where privacy needs to be sustained for a very long period of time, military data sets and all, right? If you have such data sets in the hands of attackers, even though they may not be able to decrypt it at the moment, we are saying that harvest now, decrypt later is real, it's a risk, and these malicious actors can actually harvest this data and hold on to it with the aim of decrypting it later, right? So, case study: NIST post quantum efforts, financial sector adoption is one of the case studies that we can look at. So let's talk about preparing for the quantum era. So quantum key distribution, right? Quantum key distribution, QKD, secures communication using quantum mechanics, then detects eavesdropping through quantum state disturbance. Of course, I mentioned this, that this will be very good and very applicable in areas like intrusion detection systems, right? So there is policy and preparedness. So policy, standards, funding, partnerships have to come into play for us to prepare for the quantum era. Then there is organizations, which is risk assessment, training, investment. Of course, the risk assessment is very important. So organizations have to, carry out risk assessments that are in line with the quantum era. Okay, and of course training, and then we have investment. Then let's talk about the future, right? Opportunities for enhanced security, like I said, quantum random number generation for encryption, secure networks via QKD, remember. That's quantum key distribution. Then we have ethical and societal implications, concerns, surveillance, digital inequality. Then we have need for equitable policy solutions, right? So we have to come up with these policies that will make sure that we are practicing quantum computing in a very ethical way. You can see what is happening with artificial intelligence right now, right? And deep fake and other things that are going on. So we have to quickly, now that it's still in its early stage development, we have to come up with what these policies that protect organizations, people, and data really. Then we have long-term outlook. So fault tolerant quantum computers years away. Okay, like I said, in next 5 to 15 years, some people estimate 10 to 20 years before we can actually say, okay, we have quantum computers will become mainstream, right? And if you look at it, I mean, 10 to 20 years is not really that far. If you look at it, before all your RSAs and all your ECCs and all your Diffie-Hellman and all these cryptographic algorithms that are supposedly unbreakable now, all these things will become being caked for quantum computers. So transition to quantum safe system must start now. That means we must start to train, we must start to teach others, and really just provide training for organizations so that they can start to transition to quantum safe systems. Okay, so that in the future your banks and your bank data will still be secure. All right, we must start to come up with policies, guidelines, and so on and so forth, right? So that all these things will be in place before we get to that era. Now, for the conclusion, quantum computing represents both a threat and an opportunity for cybersecurity, like I mentioned earlier. Okay, so it's a two-way street. While it has the potential to break current cryptographic systems, it also offers new tools for enhancing security. By adopting post-quantum cryptography, developing quantum key distribution systems, and implementing policy reforms, organizations and governments can mitigate the risk and harness the benefits of quantum computing. As the quantum era approaches, a proactive and collaborative approach will be essential to ensure a secure digital future. Thank you for listening. If you have any questions about quantum computer, or you enjoyed the topic and you want to contribute, you feel free to use the comment section. And of course, if you want me to present any other topic that you love in computer science, cybersecurity, or even business, just drop it in the comment section. Feel free to ask any question, and I will be here to take all your questions and answer them. Thank you for watching. See you in the next one, guys.